Alright, so let's talk a little bit about why reactions occur. Okay, so when we have a reaction, oftentimes we're mixing our two reactants and we need to predict what the products will be. Sometimes you'll see the formation of a solid. Okay, and there are different ways we classify reactions. So if we see a product that's a solid, then once we mix the two solutions together, sometimes the solution becomes cloudy as the small particles form. This is a precipitation reaction. Sometimes what you'll see is a formation of a gas. And we see that we talked about vinegar and baking soda used to form a volcano. We see bubbles form. So that's a gas formation reaction. Okay. Another is the formation of water. Now when we form water, we can't really visually see that like we can see the bubbles or we can see the formation of a solid, the precipitation. But oftentimes this is accompanied by a temperature change. And when we do see the formation of water, this is oftentimes an acid-base neutralization. So we can go into more details of what that means. We know what acids are because we've been naming them already. Okay? And finally, we could have it where it's the transfer of electrons. And when you do have a transfer of electrons, most times you'll hear us talk about a redox reaction. Okay? So let's go through and talk about the types of equations we have. So we know the types of reactions based on their products and what they do. Now let's take a look at the types of equations that we use to describe them. Okay, the first is called a synthesis or combination reaction. And basically, you can have two reactants and they combine, hence combination, to form a single product. Okay, so multiple reactants form a single product. So an example would be like when we did our sulfur. Remember how we heated up the sulfur and it reacted with the oxygen in the air and it gave us sulfur dioxide. Okay, and remember how we also had carbon and we exposed it to oxygen. This is both what we did in experiment 5, and we formed carbon dioxide. Okay, what you could do is you could have sodium metal react with chlorine gas. And when you do that, you form sodium chloride. And this is your solid salt. Okay, you can also do something like react the sulfur dioxide with water. Okay, and you'll get sulfurous acid. You can also use a gas called sulfur trioxide, react it with water, and that will give you sulfuric acid. So notice in all of these, we start off with multiple reactants. And we end up with a single product. Okay? So what's another type of reaction that we can do? We can do the opposite of combination, and that's called decomposition. Okay, and this is where you start off with a single reactant and it decomposes into multiple products. Okay, so for instance, we could take mercury 2 oxide. Oftentimes to do decomposition, not always, but oftentimes we need to heat it, so that's why we have a little triangle over our arrow, and we form mercury plus oxygen gas. So we have to balance this out. Okay, we did this in experiment 5 where we had hydrogen peroxide. Okay, and we added a catalyst, and we ended up with water and oxygen gas. Okay, if we heat up something like copper 2 carbonate, and we heated that up, whenever you see a carbonate, these tend to decompose into carbon dioxide gas, and the remainder is your other product. Okay, so if I give you something like, let's try this one, calcium carbonate, what do you think would happen when we heat it up to decompose it? Well, here's my carbonate. So we know we're going to form carbon dioxide. And then I have an oxygen and a calcium. So we form calcium oxide as my other product. So those are typical decomposition reactions. Let's go to the third one, which is called a single displacement reactions. And we use this when we work with metals and acids to see which is more reactive in the activity series. But let's go through and just first go and define what a single displacement reaction is. So if I have one substance, typically it's going to be an element, and I react it with an ionic compound, this element reacts and it'll form, displace, if it's strong enough to bump out B, and you'll get something like this. Okay, now if it's a halogen, so this is specifically for halogens, then it will displace the anion, because halogens are nonmetals and they will tend to form anions. Okay, so let's go through and go through a few reactions with just the metals and then talk about the activity series. Okay, so reactions with metals. So suppose I did zinc and I reacted that with hydrochloric acid. Okay? To do a single displacement then, the zinc will go in the position of the hydrogen and the hydrogen gets displaced. When that happens, then what we get is zinc, and we know that the ion is a +2, so zinc chloride. And then we're going to get hydrogen gas. So we need to put a 2 here to balance it out. When this occurs, this means zinc, if zinc is active enough, strong enough to displace the hydrogen, so zinc has greater activity than hydrogen. Okay, so now what would happen if I did this reaction? Suppose I took copper and I try to react it with hydrochloric acid, but I get no reaction. What this means is that copper is too weak to displace hydrogen, which means hydrogen has greater activity than copper. Okay, so based on these two results, we can say zinc has greater activity than hydrogen, but hydrogen has greater activity than copper. Okay, now why is that useful? Then suppose I wanted to run a single displacement reaction. And here's my single displacement reaction. This is what I want to run. I want to react, okay, zinc with copper. And the question is, will anything happen? So you go to your activity series and say, oh, listen, zinc is greater than hydrogen and hydrogen is greater than copper. So zinc must be greater than copper. If that's the case, if zinc is more active than copper, then it means it's strong enough to displace the copper. Okay? So what do we get? We get zinc, nitrate, and it bumped out the copper solid. So this is what you will expect to see happen when you do this single replacement reaction in lab. So we actually develop our activity series based on these series of single displacement reactions with metals. What about the halogens? Well, we do the same thing with the halogens, and that is, if you try to react chlorine, we dissolve the chlorine in water, so it's a lot like bleach, and I actually add something like potassium iodide in solution. Okay? So what happens here is that the chlorine will displace the iodine, and you get iodine plus potassium chloride. So we know that chlorine, because it does the displacement, has greater activity than iodine. Okay? What about if there's no reaction? So let me show an example with no reaction. Suppose I take iodine and I try to react it with sodium bromide. And I get no reaction. So iodine is too weak to displace the bromine. This will tell us that bromine has greater activity. Than iodine. Okay? So that's how we develop our activity series, so we know which halogen is more reactive than the others. Okay, so those are your single displacement type of reactions. And then there's a huge family of reactions that are double displacement reactions. And what we have is we have two solutions that are mixed together of ionic compounds. We have AB reacting with CD. Now, the reason we call it a double displacement is that C will combine with B, so it displaces A. A combines with D, so A displaces C. And you get AD plus CB. So in the previous list where we talked about precipitation reactions, gas formation, water formation, those are typically double displacement reactions. Okay? So let's go through and give you an example. If I gave you, let's do magnesium bromide reacting with, let's try sodium carbonate. Okay, so what are my possible products? So some people like to do outer and inner. You can do that. Just know cation first, anion second when you write your formulas. And other people, I'm a little more old-fashioned here, I like to write down my ions first, and then I always like to do a crisscross. So these are my two ions. The two here, I need two to neutralize it. I'm just writing down the ions so I know what's available from this compound. Then from sodium carbonate, I know I have a sodium. I actually have two to make it neutral, and I have a carbonate. And I like to just crisscross. Positive and positive, they're like charges, they repel. Negative and negative, like charges, they repel. Magnesium could go with the bromide, but that's our starting material. So the only other one that's new is magnesium going to carbonate. So our products would be magnesium carbonate, this is going to be a solid, plus the sodium bromide. And that's going to be aqueous. Okay? So, when we do these types of tables, you're going to be looking up what we call solubility tables to see whether or not you're going to form a solid, to predict solid formation. And what happens is that anything that's insoluble is going to form a solid. So if a substance is insoluble, it will not dissolve in water. Okay? So, now that you've written out the products, then what we're going to do is balance it. So I have one magnesium, one carbonate. But here I have 2 sodiums and 2 bromides. So you just need 2 there, and then that's balanced. So you can do outer, magnesium to the carbonate, sodium to the bromine, or inner. But be aware, the reason I put the ions down is that even though there's subscript here, this is just to tell you the number of sodium ions that you need to make a neutral compound. So there is no such thing as Na2 2+. That doesn't exist. So be aware, some of the subscripts are going to remain the same because that's what's required to write out carbonate. Other subscripts are just to tell you the number you need to make a neutral compound. So when you write it out, you're going to write out just your ion, and then that can become a coefficient. What other types of double displacement reactions do we know? Well, we also have neutralization, or we form water, okay? So remember, an acid base, an acid gives you H plus in solution. And when we talk about bases, we're going to be looking at hydroxide in solution. Okay? So if I gave you something like hydrochloric acid, and I react it with barium hydroxide, okay, what happens is this. I'm going to go ahead and do my crisscross. Hydrochloric acid, remember this is an acid, so you're going to get H plus. And Cl minus. Barium hydroxide, the barium ion is Ba2 plus. The hydroxide ion is OH minus. So if I do my crisscross, I'm going to form HOH, which is water. So let me rewrite it as H2O. And barium is a 2 plus, chloride is a -1, so I need 2 of them. Water is a liquid, barium chloride is aqueous, so those are my products, okay? And when you detect this, this is a neutralization. To detect it, you often see a temperature increase. Okay, so that's what we're looking for. So we always check our solutions with a thermometer to see whether or not we see a change in temperature. Okay, so now let's balance it. I have 1 barium, 1 chlorine, 2 chlorine. So let me put a 2 here. That means my chlorines are good. I have 2 hydrogens, 4 hydrogens, and 2 oxygens. Here I only have 1 and 2. So if I put a 2 there, then that becomes balanced. Okay, so that's an acid-base neutralization. Okay, and the last one we're going to see under the double displacement, we're going to be looking at the production of gas bubbles. Okay, so the 3 that you need to know, is it 3? You could do up to 4, but let's go through. So 1, if I start off, let's say, with sodium sulfide, and I react it with hydrochloric acid, when I do my double displacement, the H goes in front of the S, but remember sulfide is -2 and this is a +1, so I form H2S. This directly forms a gas, and you can form sodium chloride, and that's in solution. So let's balance it out. So be aware that this is the smell. Hydrogen sulfide has the smell of rotten eggs. When you form it, you're going to say gas. Okay? what happens if I used, let's say, a carbonate? So let's do, in this case, sodium bicarbonate plus HCl. Well, tentatively, you'll have this as your product. You'll have your sodium chloride, but you'll also have carbonic acid. You say, oh, is that really a reaction or is it a no reaction? But what happens is this. This is a double displacement followed by decomposition. Remember how carbonates tend to form CO2? This will decompose automatically to carbon dioxide. And remember, we take what's remaining, so that's water. And now we see that this is a gas formation reaction. Okay? So instead of writing the carbonic acid, you would just write CO2, carbon dioxide, and water. What about if we did sodium sulfite plus hydrochloric acid? Okay? Just like you get that decomposition, you're going to form sodium chloride and you'll form sulfurous acid. But sulfurous acid decomposes. It will form sulfur dioxide and water. Okay, so you want to make sure that you understand sulfurous acid will decompose. Anytime you form carbonic acid, so it doesn't have to be with bicarbonate. If you had a carbonate, if you reacted with acid, you're going to get your double displacement, and then when you form carbonic acid, that will decompose. Okay, and then if you form your hydrogen sulfide directly, that's a gas. So if you form this, it decomposes right here. If you form sulfurous acid, that decomposes to a gas right there. Okay. The last one you want to be aware of is a formation of ammonium hydroxide. So if I take ammonium chloride and I react it with sodium hydroxide, you're going to form outer ammonium hydroxide and inner sodium chloride. But what happens is this. My ammonium hydroxide decomposes to form ammonia and water. Okay, so when you encounter this reaction, you're going to write ammonia and water, and that'll be the last of your gas displacement reactions that you need to know. So you'll have those four that you want to be aware of. The last reaction type we're going to talk about is combustion. So whenever we talk about combustion reactions,